first experiment is magnetization characteristics of DC shunt generator. What is the meaning of magnetization characteristics? So, magnetization means the field characteristics of DC shunt generator. Yes. Here, simply the meaning is what is the intention of generator? Generator is production of electric power. Generally, induced EMF is induced in the generator. So, the graph between induced generator EMF and the magnetization means nothing but the field. So, the graph between, by analyzing the graph between generator EMF EG and IF is nothing but magnetization characteristics of the any generator. Any generator. So by using that magnetization characteristics, we can find out the critical field resistance and critical speed. What is the meaning of critical field resistance? Critical field resistance means, so above that resistance, the generator failed to produce the EMF. Critical speed, below that speed, the generator fail to produce the EMF. It is nothing but the critical field. By using the graph, we can find out the critical space. These are the apparatus required in that case, and these are the nameplate details. So, our main thing is just understand the circuit diagram. Circuit diagram. Our intention is to find out the generator graph between generator EMF and field current. So for that I am taking a generator. In order to find out the generator voltage, I am connecting a voltmeter here. Look at here, a graph generator, a voltmeter here. But in order to draw the graph between field and EMF, just I am taking a field. F is the field. And in order to vary this field, connecting a rheostat here. Connecting a rheostat here. So in order to get that, in order to entering into the field current, directly I am taking the field current from this supply. But in order to operate the generator is required mechanical power. That mechanical power is taken from the motor. This motor is the shunt motor. That's why a field is there. This is the field is there. A field is connected to shunt to this motor. Field is connected to shunt to this motor. But in order to adjust this field, just connecting a rheostat from the field. And but in order to operate the motor required an electrical supply. So in order to get the electrical supply, I am giving the DC supply here. This is the DC machine, DC supply. In order to operate the switch, a DPST switch is connected, and in order to avoid the short circuit and overcurrents, just connecting the two fuses across this. In order to understand how much of voltage entering into this motor, just I am connecting the voltmeter here. Voltmeter always connected parallel to that machine. So here, look at here, this is the parallel connection, field is the shunt connection across this. This gives the voltage from the supply and voltage from the motor. And to find out the current entering from the supply to the motor, a ammeter is connected here. Ammeter is connected here. And to vary the field, connecting a rheostat here. That's why in order to operate the system very proper manner, we are connecting a 3-point start. We are connecting a 3-point starter. The 3-point starter consisting of the L, F, A. L means the line current will be entering into here. From that current will be, some of the current will be supplied to the field in order to generate the field, and some current is entering into the armature. By that magnetization and the armature current, the motor will rotate. The rotating motor will be rotate the generator. The generator will generate the EMF. The generator will generate the EMF. But in order to generate the EMF, we require the field. So that's why we are connecting the field across this by using the switch. by using the switch. If you observe very clearly, in that case, so when you are starting the experiment, when you start the experiment, this switch will be open. This switch will be open, and the motor will rotates. The motor will rotate, and the generator will also rotate. The reason it is coupling. So by applying by varying this field resistance, generally field is connected is uh, minimum connected to the minimum point, minimum rheostat. The more number of flux will be entered, so less it rotates with the less speed. After that, by varying this field rheostat, we will we will fix at this motor at the rated speed. Fix at that motor speed. So generator will also rotate at the rated speed. Then the field is connected to the this field is connect field rheostat will connected to the maximum position. That's why less field will be entering into here. Then we will note down this EMF. Again, by varying the field, we will again note down this voltage. Up to we are increasing the rated field current, we are taking the readings. We are taking the readings. That's why look at the graph here. By this field current, initially it is a 0, it will generate the 20 volts. Why? Due to the residual magnetism. By increasing 0.35 170, 0.4 180, 0.4 182, up to 0.9 it will increase 231. 0.1 it will increase 231. So the increment of the field is up to the 120% of the rated voltage. 120% of the rated voltage, we will increase up to the 120% of the rated voltage. But it depends on our lab requirement. By depends on the lab requirement, we are using some conditions. Understand? This is about OCC characteristics, magnetization characteristics of the DC shunt generator. Well, here it is connected shunt, but the supply is power. Supply is separated. Understand? This is about by using this circuit diagram, we can understand the open circuit characteristics. So while calculating this experiment, while doing this experiment, we have to find out the field resistance. In order to find out the field resistance, just connect this field across here, just by using by in order connecting a ammeter across this, connecting the voltmeter across this, and by varying the DC supply by using the rheostat, we will get voltmeter and ammeter readings. So by doing the voltmeter and ammeter, we will get the field resistance. Understand what is resistance? Resistance is nothing but voltage across point and current entering into that element is nothing but the resistance. By that we can find out this. So after finding these values, just draw the graph between the field current as x-axis and generated voltage E net as the y-axis. So if you draw the graph will follow this curve. The graph will follow this curve. And after that, you will draw the two lines. You draw the two lines. This is the tangent of this curve, and another point is the straight line from this curve. Straight line from this curve. The curve which it touches, then draw this point to this center point to this curve straight line, and you will get like this. From that, you will get field resistance. Field resistance is generally by using this straight line. Field resistance is change in generated voltage. This y-axis is generated voltage, and change in field current. We will get the field resistance. So in order to get the critical speed, so by using this AB length and AC length, and with the rated speed, we will get the critical speed. So practically, if you draw this curve by doing the experiment, you will get these results. Understand? So you will get this result. These are the graphs. These are the results. Understand? So this is about theory related to the open circuit characteristics or magnetization characteristics. And the most important thing is here the field rheostat always minimum position for the motor. Here for the generator field rheostat is always maximum for the position. Right? This is about the OCC characteristics of the DC shunt generator.
So today we are going to perform and we are going to obtain the magnetization characteristics or open circuit characteristics of DC shunt generator. So we know that for the generator we require a prime mover, right? So in our laboratory most of the prime movers are shunt motors only. So here the shunt motor connection, first we need to run the shunt motor, right? So already we are familiar with the shunt motor connections. It should be run with the help of 3-point starter, right? So before explaining the circuit diagram of OCC of a DC shunt generator, let us discuss actually what we are going to find with the help of by performing OCC.
This is the motor generator set. This is the shunt generator. This is the motor. This motor is supplying mechanical input to this generator.
So for this experiment, the shunt motor is coupled with the shunt generator, but the only difference is whatever the motors till now we have discussed, they are the self-excited, right? But coming to this experiment, we want to obtain the OCC characteristics for separately excited generator. So for the separately excited shunt generator, what we are doing means for the field we are giving a separate excitation from the line, right? So from the supply we are giving a separate excitation for the field winding. So this type of generators are said to be separately excited shunt generator, right? Both are connected in parallel. So now coming to the experiment, so as per the circuit diagram we need to give the connections, right? So we are already familiar, right? We are familiar with the shunt motor connections. So shunt motor will be run with the help of 3-point starter, right? So simply MCB on. So before running the experiment, before applying the starter, we need to check the fuse conditions, right? And slowly we need to apply the starter. After applying the starter, we need to adjust the motor field rheostat in such a way that we have to get the rated speed of the DC shunt motor. So I am slowly varying the field rheostat in such a way that the motor has to get the rated speed. The rated speed of the motor is 1500 rpm. So up to 1500 rpm, we need to vary the field rheostat. Right? Okay. So up to 1500 rpm, we need to vary the field rheostat. So after that, here we are giving a separate excitation for the generator, right? So through the switch and rheostat and one ammeter. So this ammeter will measure the generator field current and this voltmeter will measure the generator armature voltage, right? Generator armature voltage. So now I am going to close the switch connected to the generator. Now if you observe, so I am opening the switch. We need to observe the residual concept. So just to observe the residual concept here, right? The voltage, this is the armature voltage, 20 volts, right? But the field current is 0. So because of the residual magnetism we are getting, right? This is the supply voltage. Now I am going to close the switch connected across the series with the field generator. So now if you observe, the field current will be there 0.2 amps and the voltage is near about 180 volts and the corresponding speed we need to observe. And this we need to repeat until the 120% of the rated voltage, right? So how to get the 120% of the rated voltage? By varying the generator field rheostat. So generator field rheostat initially should be kept at the maximum position. Now I am going to minimize the field rheostat. Then you observe the change in the voltmeter and the ammeter, field current and the terminal voltage, right? Voltage across the armature. So you are observing, right? So we need to vary this until the voltage rating will be 120%. So up to saturation we need to perform this experiment. Now after completion of this process, again we need to repeat the same process in the reverse manner. Means we have to increase the rheostat value and we need to observe the voltmeter and corresponding ammeter readings. So this is the process to get the OCC characteristics of DC shunt generator. Now after maximizing, we need to open the switch connected for the field of the DC series generator, DC shunt generator. Now we need to open the MCB. Experiment, we were observing field current of the DC shunt generator and the armature voltage across the DC shunt generator under no load. So we were getting E0 and IF. So we have to draw the graph E naught versus IF, right? So by using the graph, we need to obtain critical speed of a DC shunt generator and the critical speed of a critical speed as well as the critical field resistance of the DC shunt generator. So this is the main intention of this experiment, right? So how to find the critical field resistance and how to find the critical speed, the procedure will be explained. Already it has been involved in the manual, so go through the manual and find the critical field resistance and the critical speed. And this experiment will be performed at a constant speed, right? The speed will be a constant at 1500 rpm, our rated speed. So we need to observe only no load EMF and the field current. So by using this graph, we need to get the critical speed as well as the critical field resistance of a shunt generator, right? Thank you.